Okay. Now, so today's question, why is the Pythagorean theorem true? So, why is the Pythagorean theorem true for right triangles? So a right triangle, what is that, right? Let's draw a picture first. So we've got a nice straight line here. Notice there's like a nice corner, and in that corner we're going to have a 90-degree angle, right? Wherever we see a corner, we've got 90 degrees. Then over here, let's call this big angle A. Let's call this little angle B. Okay, now it's also labeled the sides of the triangle. So this will be little side A, opposite angle A, and this will be little side B, opposite angle B. And then opposite the 90-degree angle is our hypotenuse, which we'll call C. Now the Pythagorean theorem states that A squared plus B squared equals C squared. Now there's one or two things we're going to assume to be true here as well. What are they? So if we have a straight line, we will assume that this is 180 degrees. You might say, well, why is that 180 degrees? Draw a circle. If you cut it in half, right, what angle is the circle, right? The circle is 360 degrees. So if we cut it in half, the line that goes through it has to be 180 degrees as well. Okay. Now, also, another thing we'll be assuming without proving is that the sum of all the angles, A, B, let's call this guy big C, is going to add up to 180. So you've got a straight line is 180, and a triangle adds up to 180. That'll be very useful. Okay, now I'm going to draw a square coming off of this right triangle. They'll have length C, so if this is a square, these all have to have length C as well. Okay, what are the angles here of the square? Some of you might already know this, but one way you can convince yourself that this is true, these are all going to be 90-degree right triangles, or sorry, right angles. Now, why is it 90 degrees? Well, cut the circle in half this way now. A circle is 360 degrees. Notice each one kind of forms a corner of a square. So each one of these corners is 90 degrees. We could pull those apart, attach them in a different way, and we could create this square. So we know every single angle of the square is 90 degrees. Okay, that's useful. Now, I'm going to do something that might seem arbitrary at first. I'm going to extend this line and then drop a straight line from here. Notice we get a nice little corner again. This creates a right triangle. Okay, what is this angle, right? What could it be? Well, back here, we said that A plus B plus 90 added up to that triangle. Here we've got 90. Okay, ignore that. Here we've got A. Here we've got 90. What does this angle have to be for it to add up to 180 degrees? Well, this one back here was A plus 90 plus B was 180. So therefore, this one also has to be angle B. And by similar logic, B plus 90 plus A has to add up to a right triangle. Okay, let's continue that logic. Using that same idea, do the same thing for this triangle, right? This has to then be angle B, right triangle. This has to be angle A. A plus 90 plus B adds up to a straight line, right? 180, straight line, 180, straight line, 180. Now, what are the sides of these different triangles? I know this one has length C, length A, length B given these two angles. Here we've got a side, we've got the two angles. You know from trig, this has to have similar sides, right? So if this is angle A, opposite angle A was side A. Opposite angle A should be side A. Then similarly, we know this side and so on. We just continue that logic. Now, what is the area of this square? Think about it. What is the area of this square? Here we could write it as b plus a times b plus a, right? Here's the length, here's the width of the square. Width times length gives us the area. So the area is equal to a plus b times a plus b. Now, is there another way we could find the area of this square? Notice I've got triangle, 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 triangle. I've got 4 different triangles and a square here. Could I find the areas of these individual pieces and add them together, right? Combining them should give us the total area as well. So this is equal to, right, what is the area of a triangle? 1/2 base times height. So 1/2 base times height, right? 1/2 base times height, 1/2 base times height, 1/2 base times height. They're all the same. So we've got 4 of these triangles. So that's this one, this one, this one, this one we've taken care of, but we didn't take care of the square in the center. What's the area of the square in the center? Well, that's length times width. That's c times c. That's c squared. Ah, I now know the area one way and the area a totally different way. Okay, here you might start to see that something is going to pop out of this area formula. Let's do some arithmetic. FOIL this out, right? A times, first, outer, inner, last. A times a squared. A times b times a, b times b. Gives us the area, right, on this left side. But now it's also equal to, right, we've got 4 times 1/2 is 2ab plus c squared. We can simplify this further, right, like terms. We've got a squared plus 2ab plus b squared equals 2ab plus c squared. Now, notice we've got a similar term on both sides. We can reduce that, right? We can subtract 2ab from both sides. So we end up with a squared plus b squared equals c squared. And there we see our famous formula from before. Notice it's all derived from the fact that this is a right triangle. And if we know the angles of a square and of a straight line, we can then derive this formula, which is true for any right triangle. And it's a powerful tool to find unknown sides. So if I measure 1 or 2 lengths, I could find that third length.